All right, let's go ahead and get started. I want to welcome you back to Unit 13. This is gases, and we've been talking about three different laws that describe the nature of gases and the relationship between the variables that are important to gases, namely pressure, volume, and temperature. So we started with Boyle's law, and we said Boyle's law says that there's an inverse relationship between pressure and volume, right? If you increase the pressure, as you would in this piston here, you're going to decrease the volume. You're going to make it smaller. Now, this all assumes that temperature remains constant. And likewise, if you increase the volume, you're going to decrease the pressure, right? If you increase the volume, you decrease the pressure. Obviously, the particles are not hitting the insides of the container as frequently if the volume is increased, so the pressure is less. So we say that that is an inverse relationship. In Boyle's law, we have an inverse relationship between pressure and volume. P1V1 is equal to P2V2. Graphically, it looks something like this. As pressure increases, volume gets smaller, right? So that's Boyle's law, the relationship between pressure and volume and temperature being held constant. We went on last time to talk about Charles's law, and Charles's law was the relationship between volume and temperature. That as long as the pressure remained constant, that if temperature were increased, that the volume would increase as well. That was a direct relationship because remember that the fifth postulate of the kinetic molecular theory says that if you increase the temperature, you increase the kinetic energy. If you increase the kinetic energy, you increase the amount of banging that goes on between the particles in this movable piston here, and it pushes the piston up, making a greater volume. So volume and temperature then are directly related. We can look at that mathematically as V1 over T1 is equal to V2 over T2. Again, you're not going to have to remember the individual laws. You don't need to know Boyle's law, Charles's law, and Gay-Lussac's law individually. I'm going to show you a law in just a moment called combined gas law that's going to pull all this together. But nonetheless, this relationship between volume and temperature is a direct relationship. As the temperature increases, the volume increases as well, assuming, of course, that pressure remains constant. So it's a direct relationship, a linear relationship. And then finally, we talked about Gay-Lussac's law. And Gay-Lussac says this. It says that there's a direct relationship between temperature, and pressure, between temperature and pressure. If the volume remains constant, if you increase the temperature, you're going to increase the pressure. If you increase the temperature, you're going to increase the pressure. So for example, if I have a balloon like this, right? And this balloon has these particles in it just like that, right? And I say, okay, the volume can't change. The volume must remain constant. But I heat up the balloon, right? I heat up the balloon not to burn the sides of the balloon or the material that holds the particles in place, but I heat up the balloon. What's going to happen to the pressure? The pressure is going to increase. So we said with regard to Gay-Lussac's law was that if the temperature increases, if the volume is held constant, the pressure is going to increase as well. And we can state that mathematically as P1 over T1 is equal to P2 over T2. And graphically, as temperature increases, pressure increases, and it is a linear relationship. It's a linear relationship. All right? Now, here's the good news. The good news is that all of that can be combined into one law. It's called the combined gas law, right? And it combines Boyle's law, Charles's law, and Gay-Lussac's law into one. So if you can remember this one, you know them all, right? You don't have to distinguish between the three. So here's the combined gas law. It says P1V1 over T1 is equal to P2V2 over T2, okay? If you want, you can do the derivation, mathematical derivation of this on your own. It's really not necessary though. Just remember P1V1 over T1 is equal to P2V2 over T2. Now, that's the combined gas law. But you often will only be dealing with two variables. So for example, if the problem says, for example, well, pressure remains constant. From the first situation to the second situation, pressure is constant. Well, gee, just cancel out pressure and you're left with V1 over T1 is equal to V2 over T2. Don't have to worry about which of the laws it is, just plug numbers in, right? And likewise, if somebody says, okay, pressure remains constant, what's the relationship between volume and temperature? If pressure remains constant, we'll cross those two out. We have V1 over T1 is equal to V2 over T2, just like that. And likewise, if temperature remains constant, cross that out, and you've got P1 V1 is equal to P2 V2, okay? So that should be very helpful then in helping us to be able to do problems in which one variable is changing, or actually two variables are changing, and one is held constant. But what if we want to just take a look at a gas with nothing changing? We just want to look at a gas and say, okay, what are the parameters of this gas? What's the pressure? What's the volume? What's the number of moles? What's the temperature? For that, we're going to use something called the ideal gas law. Before we do that, let's do a problem that requires that we use the combined gas law. So again, if you know that the variable is being held constant, just cancel it from both sides of that combined gas law. So let's try a problem. Here's what it says. It says the pressure of a 1,000 milliliter sample of gas at 10 degrees Celsius increases from 700 millimeters of mercury to 900 millimeters of mercury. So we're moving up 200 millimeters of mercury and from the first situation to the second situation. It says if the volume is unchanged, that's a clue right there. When it says volume is unchanged, that tells you that V's are going to cancel from both sides of the equation. And they're asking me, what's the new temperature? So what I'm really looking for is I'm looking for T2. So the first thing we're going to do is we're going to begin with the combined gas law. This is the combined gas law. P1V1 over T1 is equal to P2V2 over T2. Now, we've been told that the volume is what remains unchanged. So we'll cancel that out. V1 and V2 are just going to cancel away just like that. And I'm going to be left with P1 over T1 is equal to P2 over T2, right? So that's Gay-Lussac's law. We're left with Gay-Lussac's law. But you don't need to know what the law is called. All you have to do is plug numbers in to arrive at the right answer. Now, I want to remind you, though, that you've been given temperature in degrees Celsius. I want to tell you once again, degrees Celsius is never good for us. Never can you plug degrees Celsius into any equation that you're going to have in this whole unit, in this whole course, in pre-AP chemistry or in AP chemistry. Will you be able to plug in degrees Celsius and get away with it? It must be degrees Kelvin. Fortunately, it's not difficult to get to degrees Kelvin. Just add 10 to that. To whatever the number you're given in degrees Celsius, just add 10 and it'll give you degrees Kelvin. So of course 10 plus 273, 283 Kelvin. So that's the temperature. Now let's write down what we know and what we want to figure out. Okay? So we know the volume. The volume is 1,000 milliliters. But it doesn't really matter because they tell us the volume doesn't change. They say in the problem the volume is constant. So we'll write it down, but it's not going to affect the problem. They said that P1 is 700 millimeters of mercury. We started with 700 millimeters of mercury, and P2 is 900 millimeters of mercury. And they tell us that T2 is, actually they say T1 is 273, but we've already added the 10 degrees, so it's 283. And temperature, don't know. That's what we're trying to figure out. We're looking for T2. So let's rearrange to get T2 by itself. Let's rearrange to get T2 by itself. So here we go. We'll start plugging in 283. Let me scroll back up so we can hopefully see these both at the same time. I'm not sure that we can. No, I guess not. But let me just show you the equation one more time and we won't forget it, okay? So this is what we've got. This is the data that we've got. So we're going to plug in now, okay? So 1,000 was the first volume. Doesn't matter though because it's V2 as well, right? P1 was 700, P2 was 900, T1 was 283. Let's plug in now. So 700, 900, 283. All right, so T2 is equal to T2 over 1 is equal to T1, which is 283, over or times 900 divided by 700, right? 900 divided by 700. That's going to give us this number. By the way, I want you to do this on your calculator right now with me. I'm going to do it myself. 283, just check this math, times 900 equals, divide that by 700, and I get 363.857, blah, blah, blah. I'm going to round off to 3 significant digits. We're going to call it 364 Kelvin. Now, what if they say, well, we want it in Celsius? Okay, subtract 273 from that. When you do that, you get 91 degrees Celsius. So the final temperature, the T2 we were looking for, is 91 degrees Celsius. So we've used the combined gas law then to answer a question when one thing was being held constant. When in this case, it was the volume. Okay? All right, now, the combined gas law, remember, is when you have something that's changing, either pressure or temperature or volume, and something else is remaining constant, one of the three. Okay? But what if we simply want to know a character? If we want to, say for example, we know the pressure and the volume and the number of moles of a gas, but we want to know the temperature, right? Nothing's changing. We want to know the temperature. Well, assuming that the gas is what we call an ideal gas, in other words, it follows the kinetic molecular theory postulates, right? Then we're going to be able to apply this law right here called the ideal gas law. And the ideal gas law is this right here. It's a very important formula in chemistry. PV equal nRT. If you have an ideal gas, what it says is that the pressure times the volume of the gas is equal to the number of moles of gas times a constant, and I'll talk about that later, times the temperature. This is the ideal gas law, a very important law in gas chemistry. PV equal nRT. Can't get away from this relationship, okay? Now let's talk a little bit about this R, because I said we would talk about it, so now's the time. Well, it's a constant, obviously, and the units are going to depend upon the units that have been used in the problem for volume and pressure. Now, the R could either be 0.0821 liter atmospheres per mole per degree Kelvin, or in some cases the R is going to be 8.325 cubic decimeter kilopascals per mole per degree Kelvin. So which one do you use? The one that's on the left or the one that's on the right? Well, it depends. If you're using liters and atmospheres, if for volume you're using liters and for pressure you're using atmospheres, you're going to use the R 0.0821 liter atmospheres per mole per degree Kelvin. But if you're using for volume cubic decimeters and for pressure kilopascals, you're going to use the R of 8.325 cubic decimeter kilopascals per mole per degree Kelvin. Okay? So that's the ideal gas law, and I think that's a good place to stop and just kind of absorb what we've learned so far. So we've talked about Boyle's law, Charles' law, Gay-Lussac's law, and we combined those into the combined gas law, and now we've looked at something called the ideal gas law, where nothing's changing. We just simply want to take a snapshot. So the ideal gas law, for example, you can determine the pressure if you know everything else, or the volume if you know everything else, or the number of moles if you know everything else, or the temperature. And remember, R is going to be dependent upon what you're using for the volume and what you're using for the pressure. It's going to be either 0.0821 liter atmospheres per mole per degree Kelvin, or it's going to be 8.325 cubic decimeter kilopascals per mole per degree Kelvin. Folks, I think that's a good place to stop, so I'll see you in the next one.